Yeah, so I'm here. I'm going to give a physics lecture on laser ion acceleration using gold nanorods. So I'm here because I use the GPU cluster to run particle and cell simulations to study um, laser ion acceleration. I'm a visiting Fulbright scholar here at the Wigner Research Center for Physics, and I'm part of the NAPLIFE project, which is the nanoplasmonic laser induced fusion energy project. And it's very interesting if you guys haven't heard of it yet, but I'm sure you have. Okay, so the general idea of this project is to use low energy lasers to accelerate ions to produce non-equilibrium nanoscale fusion reactions. This is a lot different from standard methods of producing fusion reactions, where I have some natural fusion reactions on here as well, which normally require huge energies. So this is 2 megajoules. These huge energies are required to get the temperatures and densities necessary for a fusion reaction to occur, where these 2 nuclei undergoing a reaction need to overcome the Coulomb barrier between them, the Coulomb repulsion, so they can meet. The strong force can take over and they can fuse. So we're actually studying fusion reactions occurring not in equilibrium. We're accelerating these particles with a laser similar to what would happen in like a particle accelerator, and we're trying to just collide them together on a micro scale to get them to fuse. So we're doing fusion on the femtosecond scale and the nanometer scale, just to give you a sense of scale. So we are also particularly interested in fusion reactions that are aneutronic, which basically means that they don't emit high energy neutrons when the fusion reaction occurs. This is very important because high energy neutrons are very, very difficult to stop. They're very dangerous. They're very hard to keep in the location where the reaction is occurring. So we consider a reaction like this, which is proton boron, which has a product of 3 alphas. And these 3 alphas are very easy to stop. Alpha particles have a very short stopping distance. You can even just stop them in air. So this is actually the cross-section for proton-boron fusion. The energy scale here is in keV, which is hundreds of keV is the typical energy scale for a lot of fusion reactions we look at. And if you convert this into joules, this is actually a very, very tiny energy. So before I was telling you that it requires 2 megajoules of energy to get fusion reactions to occur in equilibrium, we're using 20 millijoule lasers to try to make fusion reactions occur. If you look at the cross-section, the energy required per particle to get the reaction to happen is actually very small. It's around 1/10 of a picojoule. It's very tiny. So you can even get to this energy just with laser pointer, like a laser pointer you have in your house. It has a strong one would have around 5 millijoules. So this is huge in comparison to the scale of a nuclear reaction. The issue is this energy is not sufficiently focused to deliver that energy to a single particle. So how do we focus this laser energy so it's on a small enough scale to get a fusion reaction to occur? The first step is to use a technology that is very popular these days. We're going to focus the energy in time. We're going to compress it in time. This increases the power output of the laser by a huge amount. And again, I want to state that in our experiment, we're only using around 27 millijoules for our laser, so it's only around 10 times the energy delivered by a typical laser pointer. So this incredible increase in the power to around 5 times 10 to the 10 watts creates the acceleration, the force gradients necessary to accelerate particles on the nanoscale to get these reactions to occur. So we're compressing the pulse down to the femtosecond scale. Where femtosecond is 10 to the negative 15 seconds. So not only do we focus this laser in time, but we also focus it in space. Now, you probably know the most you can possibly focus any light is the diffraction limit. So it depends on the setup you have, but in general, it's on the order of a factor of lambda divided by 2, where lambda is the wavelength of the light. So we use around 800 nanometer light. And so our diffraction limit is down to 400 nanometers. 800 nanometer light is typical for ultra-fast pulsed laser experience. The energy density of this laser is actually pretty large. It's 1 MeV per nanometer. And when you shoot this laser, these ultra-fast laser pulses on thin targets, you get electrons that come out at around this energy, a little bit less. So the novel method used by the NapLife group is to further focus this laser in space, past the diffraction limit. The way we do that is we couple the laser to a massive electron wave on the surface of a metal. This massive electron wave is referred to as a surface plasmon resonance, or in our case, a localized surface plasmon resonance, where it's actually the laser field coupling to the electrons in the conductor and creating a combined oscillatory wave across the surface. So this allows us to focus the light even further from 400 nanometers down to only 85 nanometers. So there's still a huge barrier to overcome, even though we focus the laser light down to this very small scale. The energy of the photons in this laser are only around 2 eV. We need to get to the nuclear scale of nuclear reactions, which is around hundreds of keV. So we need to get around 50,000 of these photons to cause an effect on, say, a single proton. The solution to this is a solution that's used in many other laser experiments. We use collective electron motion. We take the laser field, we use it to accelerate electrons, and then those electrons in turn accelerate ion. So in our specific case, we have these nanorods which sit in the electric field, and as the electric field of the laser goes by, the electrons start to oscillate with this laser field like a tiny antenna. And so you can actually calculate the best size for these small nanoparticles using pretty simple scattering theory. And for a sphere, you actually get this equation here. So if you look at the denominator here, you can find metals for which the permittivity of that metal can go negative. And you can satisfy this condition that causes the denominator to diverge. So even in this classical scattering theory, you get a divergence in how much these metallic spheres will polarize in response to light for a particular wavelength. And this is actually the frequency. You solve this relation for a particular metal. This is the frequency where the plasmonic resonance occurs. So this is just the resonant frequency for oscillating these electrons across this metal for a particular shape and size. So this is actually an experiment done in our group by Attila Bonyar, where we can see that for this wavelength here, around 800 nanometers, we get a resonant absorbance of this material, where this is basically a plastic material. It's called udma tegma, filled with gold nanorods of a particular size, 85 nanometers. And we get an absorbance of light here, resonant absorbance of light. This resonant absorbance of light causes a huge increase in the electromagnetic fields around these nanorods. So the factor of 42 mentioned here is actually how much stronger the electric field around the nanorod is in comparison to the laser field. So you get a huge increase in the electric field around these tiny nanorods. So our group has a vacuum changer where we shoot a laser that's around 27 millijoules. Again, lambda is around, the wavelength of the laser is around 795. The laser is pulsed at a duration of around 10 to 120 femtoseconds, 20 to 120 femtoseconds, and we're reaching laser intensities of 10 to the 17 to 10 to the 18 watts per square centimeter. My goal is to study the tiny region where this laser hits the target, which is around a few hundred microns, or tens of microns, and study how proton and ion acceleration is occurring in this tiny region. So our goal is to introduce nanostructured targets, which include these tiny rods that I was discussing, which resonantly absorb the light, in order to enhance ion acceleration in these laser experiments. And the plasmonic resonance is really the unique part of our group. Lots of other groups use nanostructured targets, but we're the only ones using resonant ones. And there was a recent paper in 2024 about indications of proton-boron reactions in these laser experiments. So in some of the past research, this is actually a particle and cell simulation done by Istvan Pop. We can see this is proton energy and kinetic energy in MeV, that we get much, much higher proton energies when we include nanorods in the medium and when we don't. So this is just a simulation box, a nanorod in the middle. We measure proton energies coming out of the simulation. We get much higher energies when we add the nanorods. This is with nanorods, this is without. It's for different intensities. Here's an experimental result where we see with increasing intensity, we get a much higher crater volume with increasing intensity. So this is actually the control here, where there's no nanorods present in the target that we're shooting with the laser. The volume of the crater doesn't change with intensity. When we include these resonant nanorods in the target, it starts to blow up as a function of intensity. So why is this happening? These are all indications that the nanorods are causing a huge effect in the energy deposition in the laser target. So the interest to me is what is causing proton acceleration in these experiments, and how can we use our understanding of the proton acceleration to tune the laser targets to get even better proton acceleration. So the process here is basically that we're running particle and cell simulations to try to determine what forces are determining the ion energies we're getting out of this experiment. But it depends on many, many, many factors here. The laser electric field and magnetic field, the Z of the ions included in the material, the wavelength of the laser, the shape of the nanorod, all sorts of stuff. We could run a ton of simulations over this whole parameter space, but it's much better to try to create a theoretical formula that's very simple, that describes proton acceleration, so we can study it, see how it matches simulation to narrow down the parameter space that we could possibly search in. So today I'm going to talk about two forces which have become important over my research of these oscillating nanorods. One being Coulomb explosion of the nanorod, which is basically when you completely ionize a gold nanorod, it becomes unstable because there's just a bunch of positive charges everywhere. All the electrons have left from the laser pulse, pushing them away. And the whole material just starts to explode from Coulomb repulsion. The other effect is the ponderomotive force of the nanorod. So normally we think of a ponderomotive force as coming from a laser and being a force on an electron if you do any kind of laser particle interactions. But this is actually a ponderomotive force coming directly from the nanorod itself. So I'm going to talk about the ponderomotive force first. The ponderomotive force is basically a force which comes from any oscillatory electric field. And the important thing I want to mention here is that it depends on z squared of the charge feeling the force. It depends on the gradient of the electric field squared. So the idea here is when we include these nanorods into the material, we not only get an increase in the electric field due to the field enhancement around the nanorods that I showed before, but we also get a huge increase in this gradient. The gradient of the electric field normally just comes from the shape of the wave packet of the laser. Here it's coming from the shape of the nanorod. And these nanorods are very, very small, so we have a very large gradient. And using just an oscillatory like dipole spherical conductor, you can actually theoretically calculate what the ponderomotive energy gained by these particles should be around a nanorod. So just to give you an idea of what the ponderomotive force looks like, when you have an oscillating charge density across this spherical conductor as a toy model, the proton will oscillate up and down in the field, but overall it will drift towards areas of lower gradients. So if we look at the kinetic energy here, we have an oscillating kinetic energy of the proton as a function of time as it moves with the laser. But overall, the proton drifts to areas of lower gradient at large time. So we have this oscillatory position plus a drift motion. So when we run these particle simulations, we look at various outputs, electric field, charge density, number density, particle energies. But today I'm going to focus on ion energy spectra, which are most important to us because they are what we can directly observe through experiment. We're running experiments where we're shooting lasers on these nanorods, and this is basically the experimental comparison we have to the particle and cell simulations. So here is an energy spectra coming from a simulation for 10 to the 18 watts per square centimeter, a short pulse duration of 10 to the 21 femtoseconds. And we're getting ion energies around 100 kiloelectron volts. So for fusion reactions, we'd like to get slightly higher energies. So we still need to tune the experiment a little bit more, but that's why we're studying the theoretical behavior of proton acceleration here. So one thing I noticed in these simulations is for this short pulse duration, you have this motion of the protons, this gain in momentum. But even if the laser turns off here, you still get an increase in momentum. So why are you getting an increase in momentum even if the laser is turned off? After this point, the laser is turned off. There's just particles moving around in the simulation. Well, if you look at how many electrons are sitting on the gold nanorod, they very quickly decrease as the laser pulses hitting the target. And this is basically just ionization of the gold nanorod, leaving a very heavily charged gold particle sitting in the center of a plasma, and it just starts to push all the ions away, causing a Coulomb explosion. So I want to look at how important Coulomb explosion is for ion spectra of short pulse duration and high intensity. So this is actually a simulation of Coulomb explosion. There's no laser in this simulation. It's just a charged nanorod put in a simulation, no electrons on the nanorod, and it explodes. And this is the particle spectrum you get out. If we compare it to the experiment where we're actually shooting a laser on this nanorod, they're almost exactly identical. There's just a very small change in the final energies, which could be due to the random setup of the simulation. So we're seeing here that Coulomb explosion, at least for high intensity lasers and short pulse durations, is causing a majority of effect on proton acceleration from these nanorods in the laser target. So one question I thought of while I was seeing this is, why is the ponder motive force so small? With the field enhancements predicted by theory, we should be getting a huge ponder motive force on these protons, leading to a much, much larger dependence on whether the laser was actually present or not. And if you calculate the field enhancement in epoch, that's the simulation, particle and cell simulation software we use, which is completely classical, you get a very, very small field enhancement around 2 to 4, where theory predicts a factor of 40. So I wanted to study this near field enhancement effect at various intensities because it's normally only possible to measure this effect at around 10 to the 12 watts per square centimeter. It becomes very difficult at high intensities. So we calculate the field around this nanorod, the electric field, as a function of time, and average over the laser pulse to try to get an idea of what the average near field enhancement for a particular nanorod is. So we can do that for various sizes of nanorod, from spherical to the nanorod size we use in experiments to very elongated nanorods. So this is actually the size we use in experiments, and this is what a resonance side would be for vacuum. And this is actually this plot should be the same as that absorbance curve I showed you earlier, but instead of changing laser wavelength, we're just changing the size of the nanorod. So each one of these nanorods should have a different resonant wavelength for it, which is why you see this same shape absorbance peak. But you can see as the intensity is increasing, the absorbance peak is going away. We're getting a saturation of the near field enhancement as a function of intensity. So if we look at the actual field in volts per meter, the electric field at the tip of the nanorod, we can see that for low intensity, we still have the peak, but as we get higher and higher and higher, we're reaching a saturation limit at around 10 to the 13 volts per meter. So why can't the electric field of this nanorod go above, why can't the near field enhancement go above this 10 to the 13 volts per meter? Well, one field that is around this 10 to the 13 volts per meter is just the field of the completely ionized nanorod, the field that's present in the Coulomb explosion. It's around 10 to the 13 volts per meter. And in fact, this gold line here is actually the electric field for just a fully ionized nanorod. So you can see the peaked behavior of this is saturating actually at just the field of a completely ionized nanorod. So what this is, to me, what this is implying is that the near field enhancement, how much you can increase the electric field above the laser field using these small particles, is basically limited to just what the ionization field of the nanorods are. It's fairly simple. You can't get a larger electric field than when the nanorod is completely ionized. Another effect here, which could be playing a role, which just happens to be around the same field strength, is called the wave breaking field, which is referred to in wake field acceleration, which is actually a limit on if you can still have coherent electron motion given the density that's present. And if you use the electron density present around these gold nanorods, you get that the highest field you can have while still having coherent electron motion, for instance, for these oscillating nanorods, is around 10 to the 13 volts per meter as well. So in general, the conclusions I have is for very high intensity and short pulse length, the overall effect for nanorods is just Coulomb explosion. That's still a good thing for fusion because you can get very high energies from this Coulomb explosion. In fact, there are many experiments that use Coulomb explosion to generate fusion reactions. So a natural question I have is, does using plasmonic nanorods, nanorods which have a resonance frequency of the laser, is that beneficial to proton energy to cause fusion reactions to occur? That's something I'm still studying. We're also looking at using rod arrays, which seem to have a bit more of an effect from the Ponder motive force, and especially the Ponder motive force on electrons. It's incredibly large, causing huge electron energies in the simulation. And we're actually have a plan to use targets that are periodic like this in future experiments. So to use the Ponder motive force from these nanorods, we need to stick to lower intensities and longer pulse durations where the nanorod is not being ionized and the plasmonic effect is not being saturated. And in order to get very high energies, the Ponder motive force here would only be around a few keV. We need to get to hundreds of keV. So we need to have a collective effect of many nanorods, not just one, at these low intensities in order to reach fusion energies. Now, this might sound difficult, but if you can accomplish this, it would be very good because it would be unprecedented to be able to produce a fusion reaction at this intensity. So if it is possible to use this intensity and these tens of millijoules of energy to produce a fusion reaction using the coherent effect of many nanorods, that would be wonderful. That would be very, very efficient fusion if it's possible. And I want to mention that actually next week, our group is going to Szeged to perform more measurements on this experiment. So we'll get to analyze some more results and hopefully answer a few of these questions about what's actually going on inside of these laser targets. So thank you for your time. Yeah.
Thank you for the wonderful lecture, Chris. And I just want to remark that it would be very useful to know how your results scale with the energy you mentioned that the energy is 2 eV per photon, but imagine you have 2 keV per photon.
So it's like X-rays?
Yeah, I would love to know where the bound, how that scales, because not only because it's an academic, but I have this friend in Desi who wants the, to do the irradiation with the coherent X-rays, and it can go to 20, 40 keV. So we really have an opportunity to know if by any chance the oscillations which go much faster can occur and how much we gain. Intensity is not an issue because they have lots of intensity. It's a question of which is the best intensity to use to get amplification. And of course, which size is resonant? I mean, is it
For 2 keV, though, the resonance size would be incredibly small. It would be
yes,
below the
but that's
nanometer
exactly
scale.
the question. Is it still macroscopic or is it already not?
I think it would be
Yeah, so
smaller.
maybe 100 eV. Just get the optimum. Don't stop.
Yeah, I mean,
Because
it's a good question. I would like one of the things that makes me think, so you're basically suggesting to use X-rays instead of the lasers we're using now. I mean, one thing that's interesting to me is that classically, so this plasmonic effect is a quantum effect, but like a lot of quantum effects, it has a classical analog, which basically you can calculate the frequency at which these quantum oscillations will occur at. And this really depends on a permittivity and a dielectric constant. It doesn't really know about electrons. I mean, it kind of does through the plasma frequency, but in principle, maybe there are, in a way, how we can get these things to resonate is basically that we're stuck using atomic. In principle, if you have other types of matter that are on length scales that are, lower, you can have the same effect, but at other frequencies. Namely, like if you go to X-ray, I don't know. Well, I mean, there's something like, there's giant magnetoresonance of heavy nuclei, right? So maybe that's like something similar to that. I don't know. So maybe for very high energy, we can just use different sized nuclei as the rods.
Sorry, we have to move on to the next session, to the last presentation. So thanks for Christopher.
Thank you.